All right, so let's get back to geometric camera models that we were discussing. We talked about the Euclidean space. So going to review this very quickly. So remember that if we have our three-dimensional space given by the basis vectors I, j, and k, so we have our basis vectors, say I, j, and k, and we have a vector here that we called p, maybe, yep, p. Then p can be represented as, or OP rather, this O being the origin, this OP vector can be represented as x projected onto I plus y projected onto j plus z projected onto k, meaning that this is the scalar that I have to multiply my basis vector I by, the scalar I have to multiply my j basis vector by, the scalar I have to multiply my k basis vector by, right? But that we agreed that we can just write this as x, y, and z and just keep these coefficients to represent a point or vector in three-dimensional space in my coordinate system F. Okay? Now we did that for planes as well. So when I want to represent a plane instead of a vector, then I can represent it using its normal. Remember the normal, it has a 2 norm equal to 1. And therefore, AP for any 2 vectors on the plane pi, AP vector, right? So any vector from A to P here on the plane times n has to be equal to 0 because this vector AP has to be orthogonal to n. And then we had the equation of the plane, which we rewrote as we did here in tensor form or matrix vector form, and that gives us A, B, C, D times X, Y, Z. And we had a problem when we did that. The problem was, actually it should be negative D, right? The problem was that I have A times X, B times Y, C times Z, but here I'm missing something. So I have to write a 1 to have this equation complete. And that is still equals 0. And then we call this our plane pi. That defines the plane pi right here. And the other vector defines our point, right? P. Excellent. So now I have pi p equals 0. That's my equation. That defines which points, for all the points P for which this equation holds, these are points on my plane, right? Now this is called homogeneous coordinate system because of this one that we discussed. And this, therefore, is the homogeneous coordinate vector of my original vector P that I had. Now, to go back to non-homogeneous coordinate vectors, all I need to do is divide the first 3 elements by the 4th element. Okay? Simple as that. All right. We also said that there is a peculiarity on this equation, which is that it's defined up to scale. Very good, right? Because if I multiply both sides of pi p equals 0 by any scalar s, the equation still holds, right? Which means that my equation in homogeneous coordinate systems can only be defined up to a scale. All right, let's see if we can do the same thing then for spheres. So this was for planes. Now let's see how we can do that for spheres. So a sphere S of radius r. So I want to define sphere S of radius r and centered at, say, O, I assume. Yep. So obviously, you know the equation of a sphere, x squared plus y squared plus z squared equals r squared, right? Let's rewrite this in vector matrix form. So I'm going to have, let's see, x, y, z, 1. Remember that I need to write it in homogeneous coordinates. And here I'm going to have x, y, z, 1, right? Right? Okay, let's do that. Negative r, 0. Okay. And now this gives me x squared, y squared, z squared 1, right? And now I'm just missing this one here. So I can write 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative r squared. Right? Now note I could have also written my r here. I'm not going to get into this in this class, but in computer vision, if you take computer vision next year, we talk a lot about this, okay? How to do it this other way. And so on, right? You could keep defining any form that you want to like this. You could define lines, planes, spheres, quadrics, and so on, anything that you want. So I'm not going to persist, but basically this extends to anything that you want to represent. So that's the very first thing that we need to understand about coordinate systems. The other that I want to talk about today is how now do we change from a coordinate system like this that we have defined here to another coordinate system. Okay? So let's call this coordinate system A. And now I want to change the coordinate system from A to B. Okay? Let's do that. Okay. So a coordinate system A is defined by, let's see, what do we need to define any coordinate system? We need to know where the origin is in the space, right? So my vector O and my basis vectors, right? In three-dimensional space, I, j, and k. So I'm going to call this O sub A, so that specifies that this is the origin of the coordinate system A, right? Okay. IA, JA, and KA represent the three basis vectors of the A coordinate system. Yes? Excellent. Now, what does it take to define another coordinate system? Let's say B. How are we going to define another coordinate system? Well, how about OB, IB, JB, KB, right? Easy enough, right? Excellent. Now, what does this mean? Let's draw this. Imagine this is my coordinate system A, okay? So coordinate system A that has my origin, OA, my basis vector IA, JA, and KA. So IA, JA, KA. And now, let's think about my other coordinate system. Let's call it B. So I'm going to do this. This is B. This is my origin B, IB, JB, whoops, KB. So far, so good? Now, I happen to have a point P here in 3D space. Okay? And I can represent this point P using two vectors. I can represent my point B as a vector OBP, right? Or I can represent it as my vector OAP. Okay? Now note also that I have another vector I can define, which is this one right here, which is my vector OAOB. Okay, so let's write this down. This is my OBP vector. This is my OAOB vector. And this is my OAP vector. Now remember that this is how vectors are represented, right? In Euclidean space. But we prefer to write it like this, right? It's a much more convenient, much more compact way. All right, easy enough. I can write this OAP vector as PA. Now I'm going to write the A on the top left corner of P to specify the frame of reference. So this is my point P as seen or defined rather by my coordinate system A. And I can also write PV, which is my same point B defined by the coordinate system B. Okay? All right. Now, what I want to know is how can I move from one representation to the other. Now, of course, we know that from one coordinate system to the next, there can only be a rigid or Euclidean transformation, right? I can only translate and rotate my coordinate system. There's nothing else I can do. Okay, so let's start with just pure translation. So let's assume that I translate the coordinate system. So I'm going to do this. I have my coordinate system A here, IA, JA, KA, and OA, of course. And my other one here, OB, IB, JB, KB. Now this is just a simple translation or shift, right, of the OA vector onto OB, right? The origin has moved. Now consider addition, right? I know this seems very basic, but bear with me for a second, right? So when you learn addition, right, say 1 plus 1, what's 1 plus 1 equal to? And they'll say, well, if I have one marker and I have one marker, then I add them together, I have two markers. Yeah, okay, true. How about this? If I have a one-dimensional space, right, of all the natural numbers, 1, 2, actually let's start with 0. 0, 1, 2, 3, 4, 5, and so on, right, up to infinity. And I have another one, 0, 1, 2, 3, 4, 5, and so on to infinity. What is 1 plus 1 geometrically? Well, it's very easy. I start with 1 right here, right? And I place this 1 right here, okay? This is now my, you see, my set of natural numbers just placed on this other set of natural numbers. But I start at 1 because this is where what I have here, okay? And now I'm sorry, this is what I have right here, right? The first natural. So I have 1 here and 1 here. So I place the second set of natural numbers on the first one that I have from the first set, right? But now my 1 that I had here has moved to this other position, right? And this other position is a number 2. So addition, right, adding numbers is nothing else than translating these sets of natural numbers, right? The same applies to the real domain, right? So that is what we're representing here. We're representing a shift with an addition, okay? Same thing. You're shifting, you're adding. And therefore, we have this vector here, right? OA to OB vector, right? Such that if I have a point P that can be represented either as PA or as PV, right? The only difference is that to get PV from PA, I need to translate, right? Or add OA, OB, right? Make sense? So in that case, I have PV, it's equal to OA, OB vector plus PA. Right? So addition is nothing else than a translation. Now, I don't want to represent this as this with this simplified form, PB and PA, and this is still with the old form of vectors, right? I want to represent this with this format, right? So I want to have PB equals something plus PA. What's this something going to be called in this notation? What's that? BA? BAB? Is that what? I'm sorry.
From A to B.
Right, but how is it? So remember, this is the same. Okay, let me do this. So I have OAP, right? This is this vector right here, right? And I have this equals to this other vector, which is OBP, right? Plus, I have to add this, right? So if I go this plus this, I get this. So I have OA plus OB vector. Now, we know that this we can call it PA, and this we can call it PV, right? But what can we call this? Now, note the notation here. What do I keep? My actual point. And what do I do with this? What's that? Okay. OB represented in the coordinate system of A, right? Which is, obviously, this origin here to this coordinate system is nothing else than any other point in 3D space, right? Any point P, it just happens to be called OB, okay? So it's OB as seen from the coordinate system A. And note that this we know is correct because it follows this trend. From B, I have to always be going to the same coordinate system, B. Now there is a change of coordinate systems here, and from A, I stay at A, right? There has to be this flow every single time. All right, that's pure translation. Now let's consider pure rotation. So what I'm going to do next, it's assuming that there is no translation, only a rotation, okay? So this is going to be IA, JA, KA, and OA. Now let's take B. OB is obviously going to be the same as OA, right? And now let's say that IA is this one here, B, excuse me. IB is here, JB here, and KB here. Okay, so there's been a rotation of the three basis vectors, right? Now this is obviously given by a rotation matrix. And I'm going to write that this is the rotation matrix from the coordinate system A to the coordinate system B. So I can write this as the rotation from A to B. Now this is a matrix. How do I define the rotation? Well, I can define it with these angles, right? Which is nothing else than the projection of IB onto IA and JB onto JA and so on, right? So I can write this matrix. I'm actually going from A to B, so I'm going to do this. IA onto IB, JA onto IB, and KA onto IB, and IA onto JB, and then JA onto JB, and KA onto JB, and finally IA onto KB, JA to KB and KA onto KB. Okay? So here the columns represent IA, JA, KB. The rows represent IB, JB, KB. And this is the projection of one on top of the other coordinate system, right? So if you prefer, you could write this instead. It's the same thing, but you can write this as the rotation from A to B as the projection of IB, JB, KB onto IA, JA, KA, right? Both forms are the same. So that means that we project the coordinate system A, because this is the one that we've specified here, right? A, J, K, right? A onto B, right? Now, key question for you. What is the projection of B onto A? Yep. The inverse or the transpose. Yeah, the transpose. But that's correct. It's not exactly the answer I was looking for, but that's correct. Yeah, that's correct. That's good. Anyone else? Okay, let's think about this. So I have my rotation from A to B, and you said I can compute the transpose, right? It's correct, to get the projection from B to A. Why is that correct? Because that is transposing these rows with columns. So instead of having IA, JA, KA, I now have IB, JB, KB, right? And the opposite here for rows, right? So that is correct. So that is the same as, let's see, we have this form here. So I have IA, JA, KA times IB, JB, KB transpose, which is equal to, oh, actually, my bad. This is AB, sorry. So this is projecting B onto A, so this would be BA, right? Yeah, okay, sorry. So now, if I transpose this, that is the same as the rotation from A to B, right? That's what we said. Okay. So this is equal to this one thing here is equal to this one transpose, so IB, JB, KB times IA, whoops, JA, KA, right? Which is equal to the rotation from A to B, right? Okay. Which means that once we have the rotation or the projection from A to B, I automatically have the projection from B to A, right? It's the same matrix. Just need to transpose it, right? It's the same matrix. Good. Now let's see an example of this. We'll do a very simple example of this rotational case. And again, this is just pure rotation. In fact, I'm going to simplify this to a two-dimensional rotation instead of a three-dimensional rotation. So let's call this IA, JA, and KA. And now what I'm going to do in this 2D plane, you see these two basis vectors, IA and JA? Those define a plane, right? Okay. I'm going to rotate on that plane, which means I'm rotating about KA, right? Okay, so if I rotate about KA, then I end up with IB and JB, right? And this is rotated by an angle theta, whatever, just some number. Okay. Okay. Now let's see how we can represent this. Now I'm going to take this 2D plane and I'm going to redraw it here. So I'm going to do this. I have IA and JA. And the rotated vectors IB and JB, okay? And again, this angle is theta. I'm just redrawing this seen from the top. It looks clearer than in 3D, right? Okay. Now, when I apply this equation here, what is it? This one right here. What am I doing? I'm projecting one on top of the other, right? So let's do that. I'm going to do a projection, right? I'm going to multiply this one, say, on top of this, or this one on top of this, right? So if I want to represent JA onto JB, I'm going to get this projection. This is, of course, a 90-degree angle because this is the projection, the JA projected onto JB. And I'm going to have this one also here, again, 90-degree angle of IA projected onto IB, right? Okay. Now, in that case, this vector will become this vector here, right? And this is going to be given by anyone? I forget. What is this? The cosine of the angle. Very good. And this one here, the cosine of the angle, right? So JA projected onto JB, it's the cosine of the angle, and so is IA projected onto IB. Okay. So that means I can write here in my matrix cosine of theta, something else, then something else, cosine of theta, and we'll see with the other ones, right? This is because this is the entry of IA projected onto IB and JA projected onto JB, right? According to that equation that we have at the end. Yes? All right. Now we want to know this other one, which is JA projected onto IB, excuse me, right? So this is JA here projected onto JB, right? So let's see what this is like. So we want, let's see, let me redraw this, probably that will help. All right, I'm going to do this one first. I have to do two. So I have IB, JA, and K, right? I'm going to call this K. It's KA, KB are the same. Just let's call it K, right? Okay? And now I have to project JA onto IB, right? So I need to do this projection. So JA onto IB, right? This projection. Okay. And remember that this was, what was this? This angle, this is the same as this one, so this is theta, right? And therefore this is 90 minus theta, am I right? So this is 90. Yep. So this one here is then, new one? Very good, the sine of the angle. Very good. Now the other one that I have is, looks like this, IA, JB, and K. Now I need to project IA onto K, right? Maybe I should try it like this. It'll help. That means that I'm going to do this projection here, again 90 degrees. And again, this is the angle here. So that's 90 minus the angle. So this is, again, the sine of theta, right? Yes? But there is something else. What am I missing? Negative, right? Because it's on the other side, right? Okay. All right. So we have everything. This one was the sine. This one here is the negative, the sine. Now, how about Ka or K projected onto IB? What's this equal to? K projected onto IB, this one. The orthogonal vectors, therefore, 0. Same thing here, 0. This is IA projected onto K, again, 0, 0. And this is Ka projected onto Kb, which are the same, 1. Very good. Okay. These are called the Euler angles. Euler was one of the most important mathematicians of all times. His results, we will see the results of Euler over and over again, or equations derived by Euler over and over again in this course, in computer vision, in machine learning. In fact, if you've ever heard of a string theory, anyone has heard of a string theory in physics? Big thing. String theory started because of an equation that Euler derived, like a few years before string theory was invented or was discovered, whatever the case may be. Euler was a fascinating mathematician. He had so many results that it's almost impossible not to find one of his equations when you work in any area of science. And he lived in the 1700s, right? I mean, early 1700s, I believe. So just imagine. So in general, any rotation matrix like this can be written as a product of 3 elementary rotations. One about K, one about J, and one about I, right? Like this. So this is the equation that we've derived for K. If I rotate about the J axis, then the equation is, the matrix, excuse me, is exactly the same, only that it looks like this. Because now this is the one, the J. If I'm rotating about J, the J is orthogonal to I and K, right? So this is going to be 0, 0, 1, 0, negative the sine of the angle, 0, and the cosine. Excellent. So this is if I rotate about J. And if I rotate about I, then I end up with 1, 0, 0, 0, 0, the cosine, the sine, negative the sine, and the cosine. Okay. Easy enough. So you only need to remember cosine, sine, negative sine, cosine, and then just place them, right? And if you don't remember, you draw this, and it's quick and easy to find what the values are. Now, we're going to call this the rotation about k, rather, the rotation about j, and the rotation about I, right? And you can combine them as you want by multiplying one with the other and with the other. So as we did before here, remember, P as given in the coordinate system of A, it's equal to P in the coordinate system of B plus this, right? Now I'm going to represent that rotation with a product, right? So product represents the rotation. So I'm going to do PB in the pure rotational case is R PA. And now remember, there has to be consistency, right? There has to be a path from B to A to A. So I'm going to have A here, consistent with this, and B, such that I go from A to A to B, B to B, right? Yep. All right, as we have already mentioned, the inverse of a rotation matrix is equal to its transform. Transform, did I say transform? Transpose. So let's see, if I rotate from A to B, right? And now I do the inverse of this, and I rotate from A to B. That should be equal to the identity matrix, right? Same as no rotation whatsoever, right? Okay. So let's see this. If I start with a rotation from A to B, and I transpose this, and I multiply this by a rotation from A to B, what do I get? Well, I get going from A to B, right? And now, whoops, this is the transpose of this, right? So let's think about this. The rotation from A to B can be written as IA, JA, KA, right? So I'm in A and I'm going to B. So I start with my three basis vectors, but I represent now in the B coordinate system, right? Right? Now, if I transpose this, then, or if I write it in a transpose form, then this is the same as IBA transpose, JBA transpose, KBA transpose, which is what I have here, right? So therefore, this is equal to the identity matrix as well. Or better said, if you want, this is the same as rotating from A to A, right? Which obviously is the identity matrix. All right, let's see more things. The determinant of the rotation matrix is equal to 1. Think about this for a second. The determinant of the rotation matrix R is 1. What's a determinant? The determinant is nothing else than the volume, right, of the parallelepiped defined by the vectors of that matrix, right? The basis vectors, basically, I, j, and k. So if I compute the volume, so I can say that the determinant of the rotation from A to B has to be equal to compute the volume, I'll do IA in the coordinate system B dot cross product with JA in B times KA in B, right? Now, what is this equal to? That is the norm vector, right? The vector orthogonal to these two vectors, the plane defined by these two vectors, which just happens to be this vector, right? So this is this vector by itself, or square, which is the norm, which is, what's the norm of that vector? 1. There you go. Good. More things. The matrix product that we've defined here is associative, meaning that if I have a rotation R, then a rotation R prime, and then a rotation prime prime, right? If I do first this and then this, or I do this and this, whoops, they are one and the same. Now, why is this? This is a little trickier to see, but again, this is where the geometric interpretation that excuse me, that we started with addition, right? And the same with multiplication helps, okay? Now, when you look at this, it seems a little odd that this is true. And it has to be demonstrated. You need to prove for this. But in fact, if you think about this, there's no proof needed. Because what this means, right, when I apply this, what this really means is that I first rotate according to this rotation matrix. I then rotate according to this rotation matrix, and I then rotate according to this rotation matrix, right? It does not mean that I rotate with this, then with this, and then with this. No, it means I rotate with this, then with this, then with this. That is what the geometric interpretation of the rotation means, right? That's what we have done here. Right? Now, if I first do this, and then I do this and this, right? Or if you will, I do this and then this and this, that's the same as this, right? Doesn't matter. It's the same order, you see? This goes with this, which is the same as this with this, right? And this goes with this. And here, what do I do? Well, this with this, and this with this. It always goes in the same direction. Of course, it's associative. There's no change in directionality, right? The order of multiplication always goes in the same way. That's very important to note, because obviously, in general, right, it has to be said, in general, the rotation R R prime is different than R prime R. If I rotate this marker 30 degrees this way and then 10 degrees this way, right? I'm going to get the same result than if I do 10 and 30 maybe. But in general, if I do three-dimensional rotations, this one, say, and this one, or I do this one and this one, right, in the different order, I end up in different places. Duh, obviously, right? Because I'm following different path on the sphere, right? So when I rotate in 3D, that's the same as moving a point in this three-dimensional sphere, right? So if this is the center, and I start with this point, and I first rotate here, and then I rotate here, it's not the same that if I first rotate here, and then I rotate here, right? Obviously. So rotations is nothing else than moving about this S2, this sphere, right? Three-dimensional sphere. Okay. All right, so now that we know all this, let's put everything together. So I have the pure translation case, which is an addition, the pure translation case, which is a rotation. So now I'm going to write both of them in a single equation. So I'm going to consider both translation and rotation, meaning addition and multiplication. So I have, let's see, point PV, it's given by my point PA, multiply by my rotation from A to B, plus my representation of the origin A in the coordinate system B. And that is the equation that we're going to use to change from a coordinate system to another. Now, anyone can tell me one example of when I'm going to be interested in changing coordinate systems from A to B? I can't hear you, sorry. In astronomy. Okay. Yeah, that's true. That's true. How about an example in something we have in this class? Moving the camera, very good. Another example, very similar to that. Superimposing, meaning? Not one frame to the other. You're close. From one what to what? From one camera to another camera, right? Remember, how do we define a pinhole camera? It's a box with a pinhole. Where's our coordinate system of the camera? The origin is at the pinhole, and the k vector, basis vector, is pointing toward the image plane, right? If I have two cameras, or I move the camera, right? The coordinate system is at different places, so I translate it, and at different rotations with respect to one another, right? How can I change from one camera to another, from one image to another if I move the camera? That simple equation right there. Right? That's what we are going to use. Now, as we have derived before, we're not going to be working with this format. We're going to be working with matrices. So let's write this in matrix form. There's my marker. So I want to write this in matrix form. So to write this in matrix form, I need to write it in homogeneous coordinates, right? So I'm going to have PB1, and here I'm going to have PA1. And here I'm going to have some transformation matrix, as I had before with planes, with spheres, with anything else, a transformation matrix that defines the transformation from A to B. Now, in that particular case, what is this transformation from A to B equal to? Let's see. I need to multiply by something times PA. Okay, PA, I have it here. What's that something? R from A to B, right? So far, so good. I need then to multiply my number 1 with a 0 to add nothing to that, right? I'm sorry, with 0. With, yeah, with 0 here. Well, 0 is going to go here. But here with the origin O from the origin of A as seen from B, right? So let's see if I'm doing this right. PB equals RAB times PA, that's this part, plus 1 times OAB, which is this one, right? Good. And now I have a 1 here, so I need a 0 vector, right? This is a row of 3 zeros. And what do I need at the end? To get 1? A 1, right? 1 times 1, 1. There we go. So again, this is a vector with 3 zeros, right? So it's a 3 vector. This is a 3 by 3 matrix. This is a 3 vector. And my final one. All right, this result here is called a rigid or Euclidean transformation. Now, very important, very important. You need to understand this visually. I know it sounds trivial, but you need to understand this visually because this will become extremely relevant in a few lectures. Now, when I apply a rigid transformation, the angle between any two vectors is preserved, right? There's no way I can change the angle between two vectors by applying a simple rigid transformation. So here, you see this line here and that line, they're at 90 degrees, right? This and this are at 90 degrees, approximately, right? Now, if I translate this, it's still 90 degrees. If I rotate this, even in 3D, it's still 90 degrees, right? There's nothing I can do rigidly that is going to change that angle. The same goes for distances. The distance between these 2 points is going to be maintained if I translate and rotate this, right? So distances and angles are going to be preserved under rigid transformation. That's why it's called a rigid transformation or an Euclidean transformation, right? Now, to be fair, in Euclidean transformation, I can also change the scale, right? We're going to skip that detail. Now, in a few lectures, we are going to generalize this matrix T that I have here as a matrix A, a translation vector T, a row vector of zeros, and a 1. Okay. Now, when T, the transformation matrix, is non-singular, but otherwise arbitrary, we say that we have a projective transformation. Okay, projective projection. When on top of that, A is non-singular, but otherwise arbitrary, then we're going to talk about an affine transformation. And when A is defined by vectors that are orthogonal with one another, or that define a rotation matrix, we're going to talk about a rigid or Euclidean transformation. Okay? Now we're going to go from more general, T as a non-singular matrix. That's just a projective projection. That's a projective space that I've been talking about or alluding to, which we're not really going to cover in the course other than just a few comments on it. As the second aspect, the projective space is just so weird. You just have to take computer vision because it's very interesting but very weird. In the projective space, basically, because T can be any matrix, it has to be non-singular, but it can be any matrix otherwise. You can actually change angles, distances, ratios of angles, ratios of this, I mean, pretty much anything. The only thing that you cannot change in the projective space, or one of the few things that you cannot change, is the concept of straight lines. If I have a straight line and I apply a projective transformation to it, it's still going to be straight. I cannot bend it, okay? But other than that, all bets are off. Now, in the affine transformation that we will cover in this course, this T, the A in that T has to be non-singular, but otherwise it has to be T, zeros, and 1, okay? And then in that case, angles and distances are not preserved, but the ratios are, which is very interesting. So the ratio of angles, the ratio of distances, and so on, those are preserved. Parallel lines are preserved, and so on. Okay? And in the Euclidean transformation, everything is preserved. Okay? Nothing changes. In fact, when you apply a rigid transformation, nothing really happens to an object or to a space. The only difference is that instead of observing it from a coordinate system A, you're observing it from a coordinate system B. That's the only difference, right? But nothing has changed in the coordinate system. Okay. Let's see. So let's start, or let's use all this to better define the perspective camera that we defined in our first or second lecture. Okay. All right, we will define our perspective camera by specifying two types of parameters. Number one, what's called the intrinsic parameters. And number two, the extrinsic parameters. Now, the intrinsic parameters include all the parameters of your particular camera. Okay? And the extrinsic parameters are going to define the coordinate system change from the world coordinate system to your camera coordinate system. All right, let's see how this works. Let's start with number one, intrinsic parameters. So, as always, let's think about a pinhole camera model. This is my image plane, or what we can call the physical retina of the camera. I'm going to define the center point here as Z0. Now, if I go toward some point P in the three-dimensional wall, I'm going to cross my pinhole, right? Let's say that the pinhole is here, and the pinhole is called O, and I have my coordinate system here, remember, whoops. I have my coordinate system here, here, and here. And remember, these are I, J, and K, which define my X, Y, and Z coordinates of my vector, or I, J, and K vectors. This is vectors. Remember that this image is upside down, that sometimes we like to see the right side up image, which we've called the normalized image plane. I'm sorry, the image plane, the virtual image plane, which is right in front here, right? But we can also define the normalized plane, which I'm going to have here. And let me call this the normalized image plane. Which doesn't have any of the specific intrinsic parameter changes that I have in my physical retina. What are those parameters? Okay, so for a point P in the real world, remember, capital P, I'm going to get a small p, which is equal to UV, right? And this was X, Y, Z. Now, this image plane is defined by two basis vectors, right, that define the physical retina. Now, we have assumed that we can build a physical retina that's perfectly squared. I mean, that's wishful thinking, as you can imagine. In reality, these basis vectors look probably something like this, right? I'm exaggerating, obviously. With that angle, theta, between them, it's close to 90 degrees, right? Very close. I'm going to assume that in the normalized image plane, they are exactly 90 degrees. And I'm also going to set that the distance from this normalized plane to the pinhole be equal to 1. Okay? So I'm going to normalize the focal length and the angle between these basis vectors. Now, C0 at the center of the physical retina is the projection of the pinhole onto my image plane. And say C hat is the corresponding projection of the pinhole onto the normalized image plane. My point as it goes through the normalized image plane, right? It's going to be right here. I'm going to call it P hat, which has coordinates, call it U hat, V hat. Now, U hat, V hat, let's derive this. U hat, V hat are equal to X over Z and Y over Z, right? Note that I'm not using F, the focal length, because I'm assuming that the focal length is 1. So I can write that P hat, it's equal to 1 over Z. I have a matrix here, and then P and 1. Right? In homogeneous coordinates. And what's that matrix that's in between? Well, it has to be first the identity matrix, and then a zero, right? And that gives me U hat equals X over Z, and V hat equals Y over Z and 1, right? In homogeneous coordinates. Okay. So this thing here is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, right? And now I have this. I should probably add a 1 here as well. This in homogeneous coordinates. Now this is in the normalized plane, but in reality, if I have U and V, which are in the physical retina, I have to account for the focal length. So I have X over Z times F, Y over Z times F. And I'm going to multiply this by something else, which are the size of the pixels. Okay? So imagine the physical retina like this, and I have my pixels. And the pixels are of length, let's see, I'm going to say 1 over K here, and the width 1 over K and the height 1 over L, which means that I need to multiply this here by K and this by L. Okay? In fact, I can simplify this as alpha X over Z and beta Y over Z, where alpha and beta represent both the aspect ratio of the pixels in my physical retina times the focal length, right? Remember, the focal length is the distance from the pinhole to the physical retina. All right, I'm almost done. And you only need to account for this angle theta of these two vectors. Now we've already stated that they are not perfectly 90 degrees, but they're probably very close. They probably look something like this, right? Come. Now, this we can rewrite. I'm just gonna, do you want me to go over all the equations, or can just point you to the book, right? All right. They're very long, but it doesn't matter. You can rewrite this as U alpha, whoops. This comes from here, alpha xz, plus alpha the cotangent of the angle y over z, and that accounts for that distortion of that angle. And v, it's equal to beta y over z, the sine of the angle, plus v. Oops. That's it. All right, I'm done. Typically, this is all you need. However, in some instances, know that Z0 represents the image of the origin, right? The origin is nothing else than a three-dimensional point in three-dimensional space, right? Which particular point is the origin O? It's the vector 0, 0, 0, right? Yep. That means that the image point Z0 corresponds to 0, 0. But in your computer, when you read an image, 0, 0 is rarely, if ever, at the very center of the image. The 0, 0 pixel is somewhere else, right? In MATLAB, I think, if I'm not mistaken, it's the left right-hand corner. I'm sorry, the top left-hand corner, right? I think. And in other systems, it may be the bottom right-hand corner, what have you, or the right top-hand corner. But it's never at the center. So if we call this point, say that I want to translate this point right here, U0, V0, right? This left-hand top corner to this position, that's the same as we have seen before, as just adding a new number here, right? U0 and V0. And now we are done, right? So again, I'm going to use, instead of using, remember, I use these two equations to write it down in matrix form like this. Now let me use these equations to write it down in matrix form again. I'm going to do this here. So I can write, let's see, P, my point P, it's equal to some matrix K times P hat. So again, P, remember now it's UV1 given in homogeneous coordinates. And K is going to be equal to, let's see, I need alpha as the first entry. There you go. Alpha, then the cotangent, and oops, I just realized, I'm sorry, this should be negative. Good job. This one right here. It should be negative. Negative alpha, the cotangent of the angle. and then U0. 0, because there is no entry for x here. Then beta over the sine of the angle, and V0, and then 0, 0, 1. And that applied to here gives us that transformation from the normalized plane to U and V. Now, if you want to not go from the normalized plane to the physical retina, but actually from the real three-dimensional point to the physical retina, then we need to add another matrix, or we need to use another matrix, which we're going to call, or we're going to define it as with K, which maps from the normalized plane to the physical retina, and a column of zeros. And now I can write P is equal to M capital P. And I'm almost done. I just need to add the normalizing constant here, which is 1 over z. All right. There we go. Any questions? No? All right, we'll do the extrinsic parameters next, and then we'll put everything together, and we'll end up with just one matrix, okay? I'll see you Thursday. Yep. Oh, okay.